I will talk about quantum computing and quantum software, something that I've been interested in for the last 20 years. And before I do that, I would like to do a little thought experiment. So you can all close your eyes now, if you not already did that. And imagine that we are 5 years into the future. You may open your eyes now. And you just bought your very first quantum computer online in a whim. And after a few weeks, a big black box arrives at your doorstep. And now you start to get really worried. It says quantum computer, and that's all nice. But now you get a little bit worried because what on earth are you going to do with this machine? It actually was kind of expensive. And now you maybe regret a little bit that you bought it because you don't know what to do with it. And actually it turns out to be quite difficult to figure out what to do with a quantum computer. If you Google the Wikipedia page, then it turns out that programming this machine is done in a completely different way than programming your ordinary computer. And moreover, finding applications, finding problems that are suitable to be run on this computer in an advantageous way, actually also that is kind of difficult to find. And this question of buying your quantum computer and what are you going to do with it is more relevant than you might think, because we already have small quantum machines which have 10 to 20 qubits into the lab these days. And bigger ones of 50 to 100 qubits are becoming available in the really near future. And you have to realize that this sounds like a very limited amount of qubits, but you have to realize that if we want to simulate such machines on ordinary computers, we get an exponential overhead. And so between 50 and 100 qubits, there is a threshold where we cannot simulate on ordinary computers such a computer anymore. And hence, there is the potential of computing something interesting that you couldn't compute before. But before we delve into that, let me say a little bit first about quantum physics, because that's what's underlying all this. And quantum physics, that's not, you may have heard of quantum touch, which is something that's fashionable, or quantum healing, that may be also something, or maybe you have seen this movie, Quantum of Solace. Well, that's all not quantum physics. What is quantum physics is what these gentlemen were discussing in last century, in the beginning of last century, in 1927. And you see here all illustrious names like Dirac, Schrödinger, Heisenberg, but also Einstein and Bohr, and actually Lorentz, our Dutch Lorentz. And they were discussing this new theory called quantum physics, or quantum mechanics, and actually they were not agreeing on what it meant and what it implied. You may have heard Niels Bohr say, if quantum physics hasn't profoundly shocked you, you haven't understood it yet. And Albert Einstein said, God does not play dice. And Richard Feynman, not on the picture, he entered the field later, but he's very famous. He said, I think I can safely say that nobody understands quantum physics. So, if at the end of the talk you go away not understanding anything, then that's good, because that's what's supposed to happen. Okay, so quantum physics has 3 properties that I would like to discuss with you that are important for quantum computing. And those 3 properties are the superposition principle, interference, and entanglement. And I will go through these 3 quickly. So let's first dive into the superposition principle. Which says that an object can be in several states at the same time. There's a famous thought experiment of Schrödinger, who built a box, and in that box he put his cat. Well, it's a thought experiment, so he didn't really put his cat in there. And as well as the cat is a little vial with poison in the box, and a little radioactive material and a hammer, and if the radioactive material decays, it somehow hits the hammer, and then the hammer hits the vial, and the poison comes out of the vial, and the cat dies. Now, if you close the box and you don't look inside, according to quantum mechanics, if you set it up correctly, the description of this cat is that it is both dead and alive at the same time. And when you look into the box, you will actually see that it is one of the two, and then the cat is dead or is alive. Now, this sounds like crazy, and it is, but actually this has been experimentally verified on much smaller systems like photons and electrons, and also nowadays on slightly larger systems like molecules. And the idea is to use the superposition principle to computers, to really big objects. And the cat, of course, lives on, and lives on in many, many ways. So here are the Schrödingers going to the doctor, and he has good and bad news. So let's do an experiment to show you a little bit cleaner why the superposition principle is there and how it works. So here I have a little photon gun, you see here, and it shoots photons, single photons, which you can view as little bullets, and it shines it onto a beam splitter, which is like a little piece of glass. And what happens when you shine light on it, the light goes through the piece of glass and it also gets reflected. And half the time it sort of goes through, and half the time it gets reflected. So when I shoot this photon onto this little piece of glass, this beam splitter, according to quantum mechanics, the photon goes into superposition of going either through the mirror, the half mirror, and being reflected. So it goes into this superposition, very much like the cat of Schrödinger being dead and alive at the same time. And now you see on both ends I've put photodetectors, and these are detectors that detect whether a photon is there or not. It's like opening the box. And when you continue the experiment, you see that in this case detector 0 clicked, which amounts to having looked into the box and the cat is alive. And we can repeat this experiment. Again, it goes into superposition. And in this case, perhaps detector 1 clicked, and this is the same as the cat is dead. And when you did this many, many times, you find that precisely half of the times you get a 0 and half of the time you get a 1. So you get a perfect random coin this way. And actually there is a little company in Switzerland, ID Quantique, and I actually have that machine with me, that sells a little machine that does precisely that. So it puts a photon in superposition, and here's this the little box that you can see also in the picture there, and you can just connect it to your computer with a USB, and when you do that and you have the right software installed, you get a little interface. And in this case I wanted to get 1024 random bits, you can see that here, and when I did that, this is the little table of 1024 really random bits, 0 and 1. So that's really the smallest first quantum computer, I guess, that you can have. Now, so we've seen now you can be in a superposition of 2 or more states. In this case, we only saw 2. And when I observe, when I do a measurement on that system, it collapses, and you get one of the possible states that it is in a superposition in back. And you destroy the state afterwards. So it's no longer in this superposition. The cat is really dead. Now, another thing that's very important is interference of an object in superposition. And let me demonstrate that with the same experiment. And actually, you kind of all nodded in agreement that we have this superposition. But you shouldn't, right? Because this superposition is a weird thing. That shouldn't really happen. You've never seen at least I've never seen something in superposition, and I'm willing to bet that neither of you has ever seen anything in superposition. So you might as well counter it and said, well, come on, this piece of glass here, what really happened was there was no superposition, but somehow half of the time the photon went through and half of the time it was reflected, and that's just the way these little glass pieces work. And the superposition, that's all science fiction, and that didn't really happen. And rightfully so, you should have said that. But then I counter and I say, let's look at a slightly more complicated setup, which is called the Mach-Zehnder interferometer. And we see the same pieces of glass here, these beam splitters, one here and one here. And then here on either side you see real mirrors. They always reflect, so they never let go through. They always reflect the light perfectly. And now let's do the same experiment again, and let's reason in the classical way that these beam splitters are 50-50 beam splitters. What's going to happen? So let's say I shoot my photon, and let's say this time it took the upper path, so it was reflected. And now we encounter here this mirror, and I reflect, and now I'm entering the second beam splitter. And now what's going to happen? Well, you see that the situation is perfectly the same as the situation before, right? I have a single photon here that is entering this beam splitter, this 50-50 beam splitter, and so what we expect to happen is that 50% of the time detector 1 clicks and 50% of the time detector 0 clicks, right? This is what should happen if we have 50-50 beam splitters here. And now let's actually do the experiment in a lab, and let's do it, and let's see what happens. And now surprisingly, when you do it, so you shoot your photon, what happens is that never detector 1 clicks, but always detector 0 clicks. So you never see this detector 1 going off, right? So your explanation of a 50-50 beam splitter cannot hold, right? That's wrong. Actually, there is an explanation, and that's quantum mechanics, and that was, I told you, superposition. So I go in superposition here, and then these two photons arrive here at the second beam splitter, and now, and that was what I wanted to explain to you, something called interference happens. These two paths, they interfere, and they interfere in such a way that you always see detector 0 and you never see detector 1. So the photons that were to go up here, they cancel, they destructively interfere, and the photons that go here, they constructively interfere. And I don't have time to write down the mathematics. I had some slides prepared, but 30 minutes is just not enough. But you can very simply see how this works in a mathematical framework. But what you have to take away here is that I can have superposition, and I can have this interference of stuff in superposition. And now the last one is called entanglement, which is maybe the strangest of them all, but also maybe the nicest. And the way that works is best explained by the following experiment. So here you see again my photon guns, and in this black box, I've on purposely made it black, there are mirrors and little beam splitters and other gadgets that you can find on an experimental table setup of a quantum photonics guy or girl. And but it's not complicated, but you can it's a little bit too complicated for me to draw, and it would be confusing. But so imagine that there's mirrors, etc. And now I shoot these two photons into the box. And then what happens, according to quantum mechanics, is that these two photons now are entangled. I put here an orange line, but that doesn't mean there's anything there. So these photons come out, and I shoot them again at two beam splitters. And again, according to quantum mechanics, these two photons go into superposition. But now the strange thing happens. I again have these detectors on both sides. And what happens is that, in this case, detector 1 clicked on the left side, but also detector 1 clicked on the right side. Now you may say that can happen, but when you do this many times, so let's do it again. In this case, it turns out that detector 0 clicks, but on both sides the same detector clicks. And the point is that these entangled particles, they have the property that when the left is a 1, the right is a 1 as well. So the left and the right side always clicks the same detector. And so these particles are entangled, and it seems like there is some transformation of information from one side to the other side. And actually, sort of fast forwarding to what I was thinking over there, and I've been thinking this also for some time before, perhaps you can use this entanglement on these little chips on your multicores, so that maybe you can do some more efficient computation using them. But I think that's sort of maybe an interesting research project that we could look into. Anyhow, so here I have my three properties: superposition, interference, and entanglement. And this entanglement really gives you correlations that are classically not possible, or it gives you the possibility, we will see that in a few slides down the road, it will give you the opportunity to do some distributed computation a little bit more efficient than you can do classically. I also have something prepared on computer science, but I guess you all are computer scientists, so I can go quickly. We all know this founding fathers, Turing, Church, and Post. And Turing has this nice Turing machine model. And also he demonstrated that there is this problem that cannot be solved on a quantum computer, namely the halting problem. But actually we are interested in real life, not in problems whether they are solvable or not, but they should be solvable quickly, efficiently. And here's an example that we know how to solve quickly. It's the shortest path algorithm from Amsterdam, for example, to London. And this problem can be solved efficiently due to Dijkstra, He's, by the way, Dutch, and he is the only Dutchman who ever won a Turing Award, so that's also something to be proud of. But actually he did that at the same institute I'm working, and he did that in 1959. He developed this shortest path algorithm. And actually there's a nice quote of him from which was published in the Communications of the ACM in 2010, and he said, "I became the programmer of the Mathematical Center in March of 1952, and they didn't have computers yet, they were trying to build them." So see the nice parallel of the 1950s, and now in 2018, we don't have quantum computers, but we are trying to program them. And it was really important that he was doing this. And actually, what I also find intriguing is that if you slightly change the question of asking not for the shortest path, but for the longest path between two cities, then suddenly this problem becomes infeasible, and the best solutions we know, they take exponential time. And I don't have to show that here, but you know that exponential time quickly becomes really bad. If you double something 300 times, then you have some number like 2 to the 300, and this is more than the number of atoms in the known universe. So doubling a relatively few number of times really is bad. And by the way, we still don't know whether there is a fast algorithm for this longest path problem, and this goes by the name of P versus NP problem, but I guess you're all familiar with that question, and that would be also nice to solve, but that's not what I'm going to talk about now. I'm going to talk about quantum computers and merging these two revolutions, I might say, quantum physics and computer science, into something that's called quantum computers. And I guess already Turing could have done that in the 30s, because quantum physics was already known, and maybe he should have, I don't know. But it took till the 80s when Feynman and David Deutsch really put these two things on a rigorous way together. And the idea is that instead of bits, which are 0 or 1, as you all know, and you can view that in detector language as detector 0 clicks or detector 1 clicks, we have a quantum bit, which is a superposition of 0 and 1. And in this case, it really is, you have to put in mind this superposition of going through this beam splitter and being reflected by this beam splitter. So being in the superposition of two different states, 0 and 1 at the same time. And now, if you have one qubit, it can be in the superposition of two states, and every qubit you add, you double the number of states that this qubit system can be in superposition of. And so we again see this nice exponentiation, and with a mere 300 qubits, you are in a superposition, or you can be in a superposition of 2 to the 300 states. And now the idea, and here you have to take a leap of faith with me, of quantum computing is that on these superposition states, these 2 to the 300 states, on each one you can do a single computation. So you can do, in theory, 2 to the 300 parallel computations in the time you do one. Right, so that sounds really fantastic. Unfortunately, there's one little problem, and that's how are you going to get the answer out? Right, if you now look at this 2 to the 300 massive parallel computation, you will see only a single random computation. And you don't really need a quantum computer for doing that. So measuring destroys. But luckily, there was this second ingredient that I told you about, this interference ingredient, that said, if you have a system in superposition, it can interfere with itself. And this is precisely where the quantum programmer comes in. What you want to do is you want to interfere in a destructive way the computations that you're not interested in, that you don't want to see, and you want to interfere in a positive way the computation, the answer that you do want to see. And this is something that sometimes works, and sometimes it doesn't work, but we have some examples of where it works. But you realize that this is a completely different way of programming than programming a normal computer. And our focus is on how to optimally use this information and how to optimally use this trick. And I like to say that quantum programming is like composing music, where a composer takes sound waves and likes them to and interferes them in such a way that some beautiful music comes out. A quantum programmer uses these qubits in superposition and interferes them by programming the right way that useful stuff comes out. Okay, so there is a lot of progress in building qubits. I already told you that. IBM has 50 qubits in some material called solid state qubits, at least so they claim. Intel has 49. Google announced earlier this year to have 72 qubits. Now I have to take this number with a little bit of a grain of salt, but nevertheless there is a lot of progress. In the labs, Chris Monroe has demonstrated 22 qubits, and then there's a company in Canada called D-Wave who claim to have 2,000 qubits. Unfortunately, these 2,000 qubits are not very stable, but nevertheless it's quite interesting to see what you can do with them. But my focus, my idea was that all this hardware is done by experimental physicists, and we really need to put in some more computer scientists into the match. So I think now it's time to not only focus on building qubits, but also on writing the software, very much like Dijkstra was doing in the 50s of last century. And that's why in 2015 I launched, together with the University of Amsterdam, the VU University, that's the other university in Amsterdam, and the CWI, Center for Mathematics and Computer Science, my research center called QSoft, really dedicated to looking at quantum software. What can you do with this quantum computer and how do you program it? And last year we also got a nice grant from the Dutch government to work on this together with Delft and Leiden. You can see that at QSoft it sort of borders on physics, computer science and mathematics, and you see all kind of questions that we are addressing, like what can you do with these small qubit systems, that is predominantly done here. What can you do if you have bigger quantum computers available? What can you do when you have a quantum computer? How can you still have a safe cryptographic world? And here is the more foundational questions of quantum information. So you've all been wondering, and I already said this question is, what can you do with this quantum computer? And we do know a couple of things that you can do with it. And the first one is actually a little bit of bad news. This is probably also what you know. There was early on an algorithm of Peter Shor that showed that you can break, by factoring large numbers into its prime factors, you can break a lot of cryptography that's used today. So like RSA and RSA-like schemes, they're all broken. Luckily, Bennett Brassard and later Arthur Eckert showed that you can use quantum mechanics itself to repair the situation. I will say a little bit more about that also. We also showed that using this entanglement, you can have efficient communication in certain cases. You can have efficient distributed communication, computation. And this gives rise to something that's called the quantum internet and the use of entanglement over longer distances. And another application that should not be underestimated is that using this quantum computer, you can simulate nature, and nature itself is quantum mechanical. And for example, if you look at quantum chemistry and reactions of molecules and how the electrons merge with other molecules, then this whole picture is in a quantum mechanical picture, and we cannot simulate that on a normal computer because of this exponential speed up, this exponential blow up of the system. However, on a quantum computer, you can actually simulate these systems perfectly if you had a perfect quantum computer, and hence you can see things that you couldn't see before. You can compute stuff that you couldn't compute before. So let me give you one example, and I think it's kind of a nice example of how a quantum algorithm works, and you can sort of see with your own eyes why there is an advantage here. And the way I want to demonstrate it is by a random walk on the line, which is actually random walk technique is something that you can use a lot if you want to program. And the idea here is that you start here at point 0 and you flip a coin and you decide with probability half to go to the right or to the left. And then you continue doing that, right? You move on the line and each time you go to the right or to the left with probability half. You have to imagine it's a slightly more complicated graph than a line, but I want to use a line because it's more insightful. It's easier to picture. So we do this. We go left and right and we sort of move along. And when you plot a graph of what is the probability that I sit at a certain point in time, so here I'm using 250 steps, then you see that you get this nice bell curve, and you see that still the highest probability is that you haven't moved at all, that you sit in the middle, but you have moved about square root of t steps to the right and to the left with still reasonable probability. Right? So you get this nicely somewhat concentrated curve around where you started. And now let's do the same thing, but in superposition. So let's do this in a quantum way. And so here I have two registers. I have a register that says where I am, and I have a register that says whether I go left and right. But that register now I'm going to put in superposition by something that's called the Hadamard transform. And I haven't explained what it is, but you have seen it because the Hadamard transform is just this beam splitter that lets your photon go through and reflect in superposition. So I do that with this register, and what happens, I get into a 0 plus 1, right? I get in the superposition of 0 and 1. And now you can rewrite this according to the quantum mechanics and tensor computation, and you see that you are in a superposition of having a 0 in your register and having a 1 in your register. And now, depending on this red register, you move left and right. So I move left and right, and so now I'm in the superposition of point -1 and point 1 at the same time. Right? So I didn't move one way or the other, I just moved at the same time. And now you repeat, and I do this procedure again. And now actually it's interesting, so what do you think that happens? Any idea how the graph looks like? Well, I didn't, but when you program it, you get this shape. It's completely different than the classical one. It's not at all concentrated around the 0 anymore. It's asymmetric, that's also strange, but you can explain that as well. But more importantly, you said that most of the weight now sits here at the end, right? Not square root of t away, but almost t steps away from the middle. And so when you do in this way a quantum walk on the line, instead of being only square root of t away, you move linear away. They say in walk terms, they say you go ballistic. And you see here the two graphs next to each other. And the reason why it happens actually, why you don't see stuff here in the middle, why there's very little probability of ending up in the middle, is that there are paths that go to the middle, but they cancel each other. So they destructively cancel each other and you don't end up there. And there's very little paths that go here to the end in a classical way, but they cannot be cancelled, so they actually are constructively over there. And so you get a lot of cancellations in the middle, which means that stuff has to be pushed to the side. So that's the reason why this works. Okay, and since I already told you that a lot of algorithms are using this walk element in it, if you have a complicated graph and you're trying to find a marked element, then a random walk sometimes works very well. And now you can speed up all these algorithms for the particular problems in a quantum way. For example, the most famous one is this search here, where classically it takes n time to search on a graph, but on a quantum machine you can use this square root of n speed up that I just showed to you to search a little bit faster. I'm almost done, I think. So I told you that quantum computers break cryptography. And you might say that that's okay, because I don't worry, because this quantum computer that can do that is still 10 to 15 years into the future, and I'll worry about it when the time comes. But actually, that's not entirely true, because all information you send now over the internet, and it's not your credit card that people are interested in, but more sensitive information that can and will be stored by someone. And now once this quantum computer becomes available, this information can be read and can be decrypted. And so if you want your information that you send now to be still safe in 10 to 15 years from now, you actually have to change to something that we call quantum proof encryption. And so this is also a big thing that people look at. Perry is looking at his watch. I'm almost done. So I told you that this distributed computing is something that you can use using qubits or using entanglement, and here's an example of that. Here we have Alice and Bob. We use them a lot, and they want to make an appointment with each other, maybe to have lunch. And then typically what will happen these days is that you're asked to fill out the doodle or something. But actually filling out the doodle is actually the same thing as the conversation that goes on here. Namely, Alice asks Bob, are you available to meet me up for lunch on Monday? And then Bob says, no, Monday I have to go to a nice conference. but what about Tuesday? And then Alice says, no, Tuesday is not good because I have to go to the dentist. And so it goes back and forth a little while. And you can show that in a classical way, you basically have to send your whole diary over from Alice to Bob, or from Bob to Alice, or pieces thereof. Whereas if you had qubits of communication, or when you had entanglement at your disposal, you can do this much more efficiently, namely by only sending square root of your diary across. And so there are examples where this speed up in communication is even exponential. So this is a thriving area, and this is something that I thought might be interesting to use on the multicore in some way. But we're building also a small quantum network in the Netherlands, but I won't say much about that. Let me finish up by saying what are the challenges that we're facing. So the first challenge that we're facing is, what can you do with these small qubit systems? From 10 to 50 qubits, it's just proof of principle, but between 50 and 100 qubits, there actually is a possibility that you outperform any classical computer. And actually, this goes by the name of quantum supremacy. This would be the first experiment that shows that you have computed something, maybe not interesting, but something, on a quantum computer, on a small quantum device that you could not compute before. Then we're looking into small quantum networks. I think that's interesting and important. And another actually very interesting question is, how do you verify that your quantum computer computed the right thing for you? Right? If you have up to 50 qubits, you can simulate the system on your classical computer and know whether it was correct or not. But if you have something that ran on a 100 qubit computer and it said, say, 42, then how do you know that this is the right answer? And this is kind of interesting. So when we have more than a few qubits, when we have more than 100, we need to be able to do error correction, and this is something that requires more qubits. You can do this quantum distributed computing. Quantum learning theory is something that people are looking at, quantum optimization. These are all areas where we think that quantum computers can help. Maybe new quantum algorithms and quantum theorem provers, maybe something. Maybe with the quantum computer you can prove stuff that you couldn't prove before, not even if you were a fantastically smart human being. Summing up, I think it's quite exciting in the area that in the times we are living now. Quantum software and quantum computing merges these two great revolutions, quantum mechanics and computer science, and there are really endless possibilities that we don't know of, like the endless possibilities that the people in the 60s didn't know that were lying ahead of them. I also think it's quite urgent to look into quantum software now. These medium-sized computers are already there, and it addresses really urgent societal needs like drug design and energy and security. And by the way, also the big industry now becomes very interested in this, precisely this question of what can I do with the quantum computer, and is it interesting and good for my company? And I think that's something that is really interesting and needs to be discussed and be investigated further. Moreover, I think we in Europe are at a very good place to actually funnel this quantum software industry, and particularly the software and hardware industry. And saying that, let's end. And if you have any questions, please go ahead.
Thank you very much.